Today, I'm going to discuss DC electric motors. These use magnetic fields to turn electric current into rotational motion. Due to its prominence in this video, I suggest you watch my video on magnetism to understand the relation between electricity and magnetism. I'll provide a brief overview either way. Magnets have two poles, north and south. Opposite poles attract, while identical poles repel. Magnetism itself is created by moving charged particles, and current is the flow of positive charge through a wire, so current creates a magnetic field. Now we can move on to motors, which consist of several parts. The power source, such as a battery or wall socket, creates the current running through the motor. There's also the armature, which has a wire wrapped in a loop several times, creating a magnetic field connected to the axle, the commutator and brushes, which bring the current to the armature, and the field magnet, which creates the external magnetic field that drives the armature. I'm going to start with the field magnet. The field magnet can be either a permanent or electromagnet. If it is a permanent magnet, two permanent magnets are placed on opposite sides of the armature, creating a magnetic field between the magnets, which the armature interacts with. If an electromagnet is used, either the two permanent magnets could just be replaced by electromagnets, or one electromagnet can magnetize a piece of metal that is wrapped around the armature, like so. This effectively puts the armature inside a magnet. In either case, a magnetic field still runs through the armature. The electromagnet method often creates a stronger magnetic field than permanent magnets, but additional power from the battery needs to be provided to create the magnetic field in the first place. Next, we'll move on to the armature. For this, a wire is wrapped in a coil around a metal pole, which juts out of the central axle. The axle is what the rotational motion is transferred along. The armature often has several coils, but for this explanation I will focus on 2 and 3 coil motors. In either case, the coiled wire is an electromagnet, and when current runs through it, a magnetic field is created. The direction of the magnetic field depends on the direction of the current running through it. As an example, let's say the coil is near the north end of the field magnet, and current runs through the wire such that the north end of the electromagnet points out. Since the north end of the coil is closest to the north end of the field magnet, the coil gets pushed away. This causes the axle to rotate, so now the north end of the coil is pointing towards the south end of the field magnet, attracting the coil and causing the axle to rotate further. Likewise, if we have 2 coils, the other coil has its magnetic south pole pointing out and is near the south end of the field magnet. This causes that coil to also be repelled and then attracted. When the 2 coils reach the extreme point, where the north coil points toward the south field magnet and vice versa, the current switches. Now the electromagnets on the coil are reversed, bringing us back to the start of the scenario. This cycle continues as long as the motor is on. If you have 3 coils, the same basic thing happens. Each coil is repelled and then attracted by the field magnets. When an individual coil reaches its extreme end, pointing directly toward the field magnet of opposite polarity, that individual electromagnet on the coil switches directions, causing it to be repelled and then attracted again. The main difference is that the coil switching in a 3-coil motor is not simultaneous anymore. The commutator and brushes then explain why the current, and thus magnetic fields, change direction. Despite the name, the brushes aren't really brushes, but rather strips of metal that brush against the commutator. The brushes are connected to the battery, so one brush is positive while the other is negative. The commutator is effectively a split metal ring connected to the axle. If it's a 2-coil motor, the commutator is split into 2 parts. If it's 3-coil, the commutator is 3 parts, and so on depending on the number of coils. Each part of the ring is connected to 1 or 2 coils, depending on the total number of coils. Initially, one part of the ring makes contact with the positive brush, while the other part of the ring is in contact with the negative brush. If this is a 3-coil motor, the third part of the ring is not connected to a brush. As the armature spins, the commutator spins, causing the parts of the ring to flip, making contact with opposite brushes. This is how we get the perfectly timed flipping of current to inverse the magnetic fields of the coils. In the 2-coil motor, each part of the commutator is connected to one coil, and the coils themselves are connected by a wire. There is one path of current, from the positive brush to one part of the ring, to one coil, to the second coil, to the other part of the ring, and finally to the negative brush. In a 3-coil motor, each part of the commutator is connected to 2 coils, and there are 2 paths. The shorter one is from the positive brush to one part of the ring, through one coil, back to another part of the ring, and then to the negative brush. While the second path is from the positive brush to that same first part of the ring, to a different coil, to the third, not brush-connected, part of the ring, to the last coil, back to that same last piece of the ring, and to the negative brush. As the armature turns, each coil gets a chance to be the short path, giving that coil an opposite magnetic polarity to the other 2 coils on the longer path. The short path keeps changing coils, causing the coils to keep changing magnetic polarity. This matches up with when each coil reaches the extreme of the magnetic field, repeating the cycle that keeps the motor spinning. This is how a brushed DC motor works. The brushes and commutator send current to the armature, flipping the direction of the current at the proper time. The armature wire is wrapped around some number of coils, which create a magnetic field when current runs through them, with the polarity of the magnet depending on the direction of the current. These electromagnets then interact with the external field magnets, causing the axle to spin. There are also brushless DC electric motors. For these, instead of brushes and a commutator, alternating current is used to switch the magnetic polarity. The DC power is turned to AC via an inverter, which is beyond the scope of this video. Brushless motors exchange mechanical complexity for electrical complexity. By eliminating the friction between the brushes and commutator, the motors can be smaller, more powerful, and last longer. While both brushed and brushless motors require DC power, such as from a battery, there is also the universal motor, which can run on either AC or DC power. The difference for these is that the field magnets must be electromagnets, and they are connected directly to the brushes. So power goes from the source to the field magnet, to one brush, through the commutator and armature, back to the other brush, and then back to the power source. This ensures that the magnetic fields of both the field magnet and armature flip simultaneously as the current alternates flow direction. Despite these differences between brushed, brushless, and universal motors, all 3 work as I've described previously. While I explained DC motors with 2 or 3 coils, most motors have several coils, in the neighborhood of 8 or more. The larger the number of coils, the smoother the rotation of the motor. the same basic principles still all apply, there are just many more coils and commutator splits. Nevertheless, hope you enjoyed it, hope you learned something, and see ya.